Next, we need to talk about complex numbers. A complex number is simply a real number added to an imaginary number. So it's going to have two parts, a plus bi, where a is the real number part and bi is the imaginary number part. All complex numbers must be written in the form a plus bi, where the real part is in front and the imaginary part is in the back. So if I have 5 plus 2i, the real part is 5 and the imaginary part is 2i. Well, what if I just had 12i? Well, this is a purely imaginary number. There is no real part number. So the real part would be 0 and the imaginary part would be 12i. Another way of thinking about that is like 0 plus 12i. Okay, for x plus 4 minus 3i, clearly the minus 3i is the imaginary part, so the entire variable and the expression x plus 4 is the entire real part. Okay, and then negative 14, that's a real number because it doesn't have an I, so it doesn't have any imaginary part, so you have a 0 for that. It's as if you were saying negative 14 plus 0i. Okay, so we're going to learn how to add and subtract complex numbers. When we add and subtract complex numbers, we simply add or subtract the real parts and then add or subtract the imaginary parts. It's very similar to adding or subtracting variables. But the thing that you must remember is you have to put it in a plus bi form, meaning the real part has to come first and the imaginary part has to come second. So here I have the real parts, negative 4 plus 3, that gets me negative 1 when I add them. And then the imaginary parts are 7i plus 2i, and that gets me 9i. Very simple. The next one is a little bit more complicated because it's a subtract and it has a parentheses in it. That means that I need to take the negative 1 and distribute that negative all the way through. So it's going to be 3 minus 5i minus 7 minus 4i, because the negative 1 distributes to both. Very similar to variables. The only difference is that the variable usually would go in the front and the number would go in the back, but in this case the number goes in the front and the imaginary part goes in the back. So let's see, my real parts on the next one. 3 and negative 7, that makes negative 4. The real parts are negative 5i and negative 4i, which makes negative 9i. And that's it. Okay, so the next one has a complex number minus. So what are we going to do with the minus? Distribute the negative. Negative times 1 is negative 1. Negative times a negative 4 is a positive 4i. And then if you distribute a positive, it doesn't really do much. So we're just going to go ahead and bring that down as well. So then I'm looking for all real number parts. 2 minus 1 is 1, and 1 minus 2 more is negative 1. That's for the real part. For the imaginary part, I'm going to underline those in blue. 3 plus 4 is 7, and 7 plus 3 more is 10. So that's how you add and subtract complex numbers. Very, very simple because you've done it with variables. Just make sure the I is in the back. Okay, so next we're going to be talking about simplifying expressions with radicals and complex numbers. In this class, you're going to be solving equations whose answers have radicals and complex numbers in them, especially when we're doing quadratic equations in your near future. So you will need to be able to simplify these answers, which is what we're going to practice today. All we practice today is the simplifying, but you're going to actually be using the simplifying very soon. There is a symbol that we need to introduce. We talked a little bit about it earlier. The symbol plus or minus means the positive and the negative part. And a lot of these problems are going to have a plus or minus in them, so I just want you to know what that means. Sometimes we'll break them up and sometimes we won't, and we'll discuss that. Some expressions with radicals may have answers that are integers. like 5 or -7. Okay. Some expressions with radicals may have answers that are irrational. Irrational means we have a radical in it that doesn't stop or repeat, and so you can't actually write it down like a whole number, like an integer, but we can leave it in this form, 2 plus or minus root 7 over 4. And then even more expressions may have answers that are complex, like 5 plus or minus 4i. The thing here, you can't add or subtract them, so you're just going to leave them there with a plus or minus because of the I. Now, if it has a radical or if it has an I, a lot of students are like, these are going to be harder. I like the integer ones better. Well, it turns out these are a little bit easier because you don't have to do quite as many steps. The integer one takes a little bit more time. So I have 3 examples here, one of each type. Okay, so let's take a look at the first one. Now sometimes you approach the problem and you're not like, oh, I know this is going to be an integer, or oh, I know this is going to be complex. You actually have to look at it a little bit. So the square root of 16. We just practiced square roots. So square root of 16 is a whole number. That's plain 4. So we have 3 plus or minus root 16, which reduces to 3 plus or minus 4. Now, because I happen to know what 3 plus 4 is, and I know what 3 minus 4 is, I am required to break this up and get the 2 integer answers. Because this came out with no radical or no I actually have to keep going. So what is 3 plus 4? 3 plus 4 is 7, and 3 minus 4 is -1. That's what the plus or minus means. It means both the plus part and the minus part. And because you happen to know what 3 plus 4 is and 3 minus 4 is, you actually have to work it out. So the answer here is 7 and -1. The plus or minus is going to tell you that you have 2 answers, and here are your 2 answers. Now this came out to be an integer. Example. So go ahead and label this integers. We might not have known that initially, but I needed you to understand that you just have to practice and see what it is. So in the next one it says 3 plus or minus root 18, which is similar to the first one, but root 18 breaks down differently than root 16. Root 16 was plain 4 because we had that one memorized. Root 18 is one of those that you have to break down because it's not in my perfect square list. So 9 times 2, 332. So the 3 goes out of the house. The 2 stays home because he's a single, he stays home. And then I'm going to bring the root 3 plus or minus down. So do I know what 3 plus 3 root 2 is? Can I combine those? Well, no. How come you can't add them? Well, this part's a whole number and this part's a radical, and they're not like radicals. So because they're not like radicals, I can't add them, which means that's my answer. So I kind of like this one because you don't have to keep going. You can just stop and leave it plus or minus. That plus or minus tells the reader the answer is 3 plus 3 root 3 and 3 minus 3 root 3 all at the same time without having to write it out twice, because mathematicians are notoriously lazy, and that's just one lazy thing that they do. They just put plus or minus, and that means both. So as long as the reader and the writer both know what they're talking about, then we're allowed to do shortcuts like that. What kind of example is this? This is irrational. The reason it's irrational is because we have a radical left in the answer that can't reduce. Alright, so look at the next problem. Very similar to the other two. 3 plus or minus the square root of -16. So we're going to go ahead and reduce the -16. The root negative is, whenever you have a square root of a negative, that becomes an I, right? So the square root of 16 is 4, the square root of negative is I. So we have this reducing to 3 plus or minus I. Again, I can't add 3 plus 4i because one's a real part and one's an imaginary part. So I can't add those. I can't add 4 minus 3i, so I can just leave it in the shortcut method for 3 plus or minus 4i. What kind of example is this? It's a complex example, okay? So I just wanted you to see the 3 different types of answers that you'll be getting when you're trying to solve quadratics. And so today we're just going to practice reducing those. Now one more thing we need to talk about is sometimes, often, these expressions are going to have fractions. Some fractions can be reduced while others can't be reduced, so I want you to know the difference between them. There's two ways of doing this. Let's see. So the first way is if you are trying to reduce, you see this 4, this 2, and this 6. 4, 2, and 6 all have a common factor. So what I can do is I can factor something out of the top, just like we did when we did rationals. So we have 4 divided by 2 is 2, plus or minus 2i divided by 2, which is I, over 6. Now the 2 and the 6 can reduce, which is 1 and 3. So my reduced answer is 2 plus or minus I over 3. Okay? Now, 2 plus or minus I over 3. Because it has an I in it, we need to split it up. So we have 2 over 3 plus or minus, there's an invisible 1 here, 1 over 3i. Okay? So that's our reduced answer. 2/3 plus or minus 1/3 I. The I can either go on the top or out into the side. So that's one way of doing it. Factor and then reduce. Okay? The other way that some people like, I prefer, you just have to get good at it. You gotta practice at it, okay? Again, you're looking at 4, 2, and 6. If you can have 4, 2, and 6, and you see that there is a common factor here, I can see that 4, 2, and 6 all divide by 2. Well, what you can do, as long as you treat everybody in the top and everyone in the bottom the same, all terms, you can just divide it by 2 in your head and get 2. Divide by 2, you get 1. Divide by 2, you get 3. And you'll get 2 plus or minus 1i over 3, and then you can split it up. This eliminates the process of having to factor out the 2, but technically that's what you're doing. The more mathematically correct is the first way, but the second way is also correct, but it is basically doing the same thing, dish shortcut. Okay, so let's take a look at the next problem. 4, 3, and 6. Can 4, 3, and 6 have a common factor? Well, no, they don't have anything that's common that they all can divide by. Do you see that? 4, 3, and 6 don't all divide it by anything. So what you're going to do is, because it doesn't reduce, it has an I, and so because it has an I, we need to separate it. So we're going to do 4/6 plus or minus 3/6 I. And now that you've separated it, the 4/6 can reduce, and the 3/6 can reduce to 1/2. And so that's going to be my reduced answer. The reason we had to separate it is because it has to be in A plus BI form. So anything with an I, you need to separate the top into 2 fractions. Okay. Now take a look at the next two. Do the next two have I's in it? No, they have radicals. So we're allowed to keep these in one big fraction, or you can split them up. It doesn't really matter. So what we're looking at is the 6, the 9, and the 12, not the root 2. The root 2 is on the inside and it's kind of protected there. So I'm just looking at all of the coefficients, 6, 9, and 12. Can 6, 9, and 12 have a common factor? Yes, they do. So if I factor a 3 out of the top, that gets me 2 plus or minus 3 root 2 over 12. Now that I've factored it, now the 3 and the 12 can reduce, and this reduces to 2 plus or minus 3 root 2 over 4. The other way you could have done this, same thing, about the same amount of steps, but if you want to think about it this way, if you just look at the 6, the 9, and the 12, and you say, oh yeah, 6, 9, and 12 all can be divided by 3. So you're just going to go ahead and divide by 3, you get 2. Divide by 3, you get 3, and divide by 3, you get 4, and I still get 2 plus or minus 3 root 2 over 4. Now I'm not going to bother breaking this up into 2 fractions because I'm not required to, so I'm just going to go ahead and leave it that way. If you really want to, you could split it up to 2/4 plus or minus 3 root 2 over 4. But what happens is you're required, now that you've split it up, to reduce that fraction. So this is acceptable, but so is the first one we did. So I would stick with the first one. I'm not going to split it up if I don't have to, because then I have to do more reducing. If it has an I, you need to split the top into two fractions. Why? So that they can be an A plus BI form. Okay? Whereas the other two, they don't need to, so I'm not going to even bother. Alright, let's take a look at the last one here. 6, 9, and 11. Can 6, 9, and 11 all be divided by the same number? 11's not helping here at all. So there's nothing to be reduced here at all. You are totally welcome to just leave it as is, okay? So this doesn't reduce at all. And that's how I would leave it. Again, there's no need to separate the two terms in the top and to make them into two fractions because there's no I. Now, if you must, you could separate them into two fractions if you want. It's not wrong, it's just more work. If 6/11ths reduce, you would do that. If 9/11ths reduce, you could do that. But in this case, nothing really reduces here at all. So split it up, not split it up. Either one works, so I would not split it up just because it's less work for me.